Nuclear fission. It is a process in which a heavy nucleus splits into two smaller fragments, and in the process a large amount of energy is released, and that process is known as nuclear fission. It is observed that when a neutron bombards with a heavy nucleus such as uranium, then it splits into two nearly equal fragments, and in the process energy is also released, and that process is known as nuclear fission. Generally, uranium nucleus, let us consider the equation U-235. When it is bombarded with a neutron, results in a complex uranium nucleus, and this is unstable and splits into two other nuclei. One is barium, another is krypton, and in that process three more neutrons are emitted, and with the emission of large amount of energy, that Q stands for the energy released in the process. See here, this equation tells that you have a uranium nucleus which is a heavy nucleus, and it is bombarded with a neutron. Then the neutron is totally absorbed by the uranium nucleus, and a compound nucleus is obtained with a mass of 236. Since this is highly unstable, it immediately splits into two nearly equal fragments. One is barium nucleus, another is krypton nucleus. Then in that process three more neutrons are emitted, and also a large amount of energy is also released in the process, and this process is known as nuclear fission. From where that amount of energy is coming into picture is, if you determine the mass of interacting nuclei, that is before the fission process, whatever the nuclei that are there, if you consider that mass, it is large when compared to the products that are obtained after the fission process. The products are barium, krypton and three more neutrons. If you calculate the total mass of this one and this one, it is observed that the before the process, fission process, the mass is more than the mass of the product nuclei. The difference in the mass is converted into energy according to Einstein's equation, E equal to mc square, and that is what we got here, energy Q, the Q value. Generally, if you take the masses of interacting particles before the fission process, it comes out to be 236.0526 AMU. That's the total mass of the uranium 235 and neutron before the fission process. And after the fission process, whatever the products which you got, and if you consider the total mass of all the three, then what you will get is 235.8306 AMU. Obviously, you can see this mass is large and this is relatively less. If you take the difference between these two masses, you will get 0.222 AMU. That is the difference in the masses. For each one AMU, the corresponding energy is 931 million electron volt. That is calculated using E equal to mc square principle itself. So if you convert this mass into energy multiplied by 0.222 multiplied by 931 million electron volts will give you approximately 200 million electron volt. Exact value will be about 206.5 million electron volts, but generally in a fission process we take it as an approximate 200 million electron volt. That's the amount of energy released in a fission process. See, the energy released in the fission process can also be calculated in a different manner. Like for a medium size nucleus, the binding energy per nucleon is relatively large when compared to heavy nucleus. Like for example, if you take uranium nucleus, the value of binding energy per nucleon is about 7.6 million electron volt. Whereas if you consider the product nuclei in case of fission process, barium and krypton, for them the binding energy per nucleon is about 8.5 million electron volts. So this difference, if you take 8.5 minus 7.6, that comes out to be 0.9 million electron volt. See, the difference between these two binding energies per nucleon is 8.5 minus 7.6, that will be equal to 0.9 million electron volts. Now the total number of nucleons which are interacting in the process, the fission process, is 236. That is 235 is the mass number of uranium nucleus, and then 1 neutron. Put together the number of nucleons which are interacting is 236. So the total energy released in the process will be 236 multiplied by 0.9 million electron volt per each nucleon. So that will give you once again about 200 million electron volt. So in this process also we can determine the amount of energy released in fission process, which comes out to be 200 million electron volt. Now see, in case of fission process, the amount of energy is released is enormous. For example, if you consider 200 million electron volt, that is only for one fission process. But if you take let us say 1 kg of uranium, you will have a large number of atoms or nuclei of uranium. If all of them are undergoing fission process, you can imagine what is the energy released in the entire process. We will try to calculate the amount of energy released when 1 kg of uranium undergoes fission. Like in 1 kg of uranium, the number of atoms this is equal to 6.025 multiplied by 10 power 26, that is Avogadro number, divided by 235, that is the mass number of uranium nucleus. So this will be the number of atoms that is contained within 1 kg of uranium. If all of them are undergoing fission process, and we know that each fission results in 200 million electron volts of energy. So naturally this many fissions multiplied by 200 million electron volts, that will be the energy. If we calculate that one, it comes out to be 5.13 into 10 power 26, that is the energy released. And we can convert this into joules also. This is a million electron volt, and 1 electron volt is equal to 1.6 into 10 power minus 19 joules. Now suppose if you take 1 million electron volt, million stands for 10 power 6, so this expression becomes 1.6 into 10 power minus 13 joules. That is per each million electron volt when converted into joules. So this much of energy, if you convert into joules, what it will be? 5.13 multiplied by 10 power 26 multiplied by 1.6 into 10 power minus 13. That is the amount of energy released when 1 kg of uranium undergoes fission process. Generally, electricity, commercial electricity is measured in kilowatt hour. 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. So if you divide this one with 3.6 into 10 power 6, that will give you in terms of kilowatt hours, that is the commercial unit of electric energy. This will give you 2.26 multiplied by 10 power 7 kilowatt hour. You can see how large the energy is. 10 power 7 kilowatt hours, you can say 10 power 7 of the order of 10 power 7 units of electrical energy that is produced. It's enormous amount of energy produced just with 1 kg of uranium. If you want to produce the same amount of energy using conventional methods like combustion of coal, you require some million tons of coal to be burned to obtain the same amount of energy which you got from just 1 kg of uranium. That is the significance of nuclear power.